All right, guys, so what we're going to be talking about today is a method that if you had a calculator, honestly, it actually wouldn't help you either. This is one method that we use to make an approximation of something, but it doesn't tell us exactly what that is, and you'll see what I'm talking about in just a second. But this method is what is known as Euler's method. Now, in order to kind of introduce this, if you remember, once upon a time, we talked about problems like this, where we had dy dx equals 2x divided by 3y in the point 0, 2, and if we wanted to find the original function, we just followed some steps, like we get the y's to one side, we get the x's to the other, and I'm not going to go through all of these because this isn't exactly what we're going to do. Then we would take the antiderivative of both sides, so I had like 3y squared over 2 is equal to x squared. Then we had the plus c. Then we would take this point, we would plug it back in to find the c. Once we found that c, we got the y all by itself, and that gave us our original function. And one of the key parts to these problems, and again, this is why I stopped right here, is knowing that I can separate these two variables using multiplication or division. In other words, I can get the y's over to the left and I can get the x's over to the right without any issue because I can just use multiplication or division to do that. The problem is sometimes our derivative formula that has x's and y's mixed together cannot be separated in that way. We can't use multiplication or division to separate them. Like in this case, I've got dy dx equals x plus y, and again, I've got like an initial point, but if I wanted to find out what the original function was at x equals 3, I would run into an issue because I don't have a way to take the antiderivative. Now, the one thing that is true here, even though I'm looking for f of 3, is there's not a way that we can actually find out what that function value is going to be. But instead, there's a method that we can use that uses the idea of a tangent line in order to kind of estimate what that function value is going to be. So let me kind of explain what that is going to be. The first thing is we need to understand that f of 2 equals 0 is very important. That means that that point is on the graph, and I'm trying to figure out what f of 3 is. So it's kind of like I've got f of 2 equals 0 right here, so that's like the point 2 zeros on the graph, and I want to estimate what the y value is going to be when x equals 3. So I don't know if the graph's going to move up or down, but that's our idea behind what it is that we are going to do. So the idea here is this, and here's kind of a picture to illustrate what's going on. And again, these aren't the exact function values that we were talking about, and there are steps for us to follow, and that part's kind of nice. We know, like, let's say this blue function, or this blue graph, is what the function actually looks like. Now, I know that, well, we don't know that that's what it actually is, but let's say that that's kind of what it looked like. The idea that we're going to use here is we're going to say, okay, I know one point that exists on the graph, so I am going to write the equation of the tangent line at that point. And then what's going to happen is we are going to use that tangent line equation to find an x value, or excuse me, to find a y value at a prescribed x value that's a little bit further along the function. Now you'll notice that that x value that I find the function at, that's not exactly what the y value is. But if I were to then create another line, and this is where it gets a little bit complicated, using the slope of the tangent line at that point, because again, I have a derivative. So if I were to create, it's not necessarily a tangent line, but I'm going to use the slope formula to find another sort of tangent line on a second interval, and then do it again and do it again. This is not a perfect estimate as to what the y value is, but you'll notice that each of these like mini tangent lines that we have, every one of them gives us at least an approximation as to what the y value will be along the way, because it behaves in a similar manner, to what the function is actually doing. Now, I know, again, that's a little bit complicated, so let me kind of break that down into the steps that we're going to follow, okay? What we're going to do is, at the point given to us, we are going to find the slope of the tangent line, okay? Now, what's going to happen is you're going to be told where to start and where to end, and then you'll be told how many steps you're going to have to take to find the new function value. So basically, that's how much your x value is going to change by every single time. What we're going to do that is we are going to, again, create a small tangent line to estimate what the next function value is going to be. Now these steps, and again, you can pause it right here if you want to. It's much easier to show you what is happening in these steps to estimate what is going on. So let me give you an example, okay? So back to our problem, same one we had before. We've got dy dx is equal to x plus y, and we know that f of 2 is equal to 0. So at f of 2, so I know the point 2, 0 is on the graph. Now what I'm going to do is, I notice, and we're going to do a bunch of steps just so we can kind of get used to it here, but I want to approximate f of 3. Normally you don't have to do this many steps in a problem to understand what's going on, but again, I want to make sure we understand it, so we're going to do a couple of extra steps here to understand overall what's happening in the problem. So what I'm going to do is, you'll notice that my steps are going to go up by 0.2. It tells us that. So my change in x is going to be 0.2. So what that means is, I'm going to go from 2 up to 2.2 is going to be my next x value. Now what I need to do is, I'm going to use the equation of this tangent line that I'm about to make to try and guess, or try and estimate, excuse me, what the original function value would be when x equals 2.2. If you remember, the equation of any tangent line, of any line, including the tangent line, is y minus y1 is equal to m times x minus x1. I am writing the equation of the tangent line at x equals 2 and y equals 0. So I'd have y minus 0 is equal to m, and we'll talk about that in just a second, times x minus 2. Now remember, the derivative is a formula that allows us to find the slope of the tangent line. So I just go 2 plus 0 is 2. That is my slope. So that is the equation of this tangent line that I've just drawn right here. Okay, and it's just a rough estimate is what it is. But now what I can do is I can say y is equal to 2 times the x value that I want. I'm using this line to estimate what the y value is going to be right there. So I get 2.2 minus 2, which is 2 times 0.2, which gives me 0.4. So this y value right here is 0.4. Now what we're going to do, so that was our first one. Now what we're going to do is we're going to do the exact same thing, but we're going to use this point as our new point that we're going to put on our, to create our equation of our tangent line. So I'm going to go y minus 0.4 is equal to the slope that we'll get to in just a second, multiplied by x minus 2.2. Well, to find the slope, what I'm going to do is I just need to use this equation right here, but instead of using 2 and 0, now I'm going to use 2.2 and 0.4. So what I do is 2.2 plus 0.4 is 2.6. So now this is an equation, and again, this is a little bit confusing because it's not actually a tangent line, but it's another line that has a different slope than we had before. It's actually a little bit steeper this time, so it's 2.6 instead of 2. And what I'm going to do is use that equation to try and estimate what's going to happen at 2.4. So the way that I do that is I would put 2.4 in here. Oops, 2.4 minus 2.2. Then I've got 2.6 times that. Then I've got y minus 0.4 is equal to that. I get 0.2 times 2.6. When I put that into my calculator, 2.6 times 0.2 gives us 0.52. So I get 0.52 here is equal to y minus 0.4. Then I add the y value over. So I get 0.52 plus 0.4 gives me a y value of 0.92. Now there's a couple things that you'll notice here that are always going to be true as we continue to do this. And so there's actually a formula that we can use that kind of allows us to find, without having to manipulate this nearly as much. You'll notice every single time I find my slope at the point in question. But every one of these, like 2.2 minus 2 and 2.4 minus 2.2, that is always how much your x value changes by. So what I have is the change in x multiplied by our slope. And then what we do to get the y by itself every time is just add the y value over. So if I'm looking for a new y value, I would just take the previous y value plus the slope at the point that we're looking at multiplied by our change in x. So if I wanted to know the next one at 2.6, so if I want to know at 2.6 here, I could say, all right, to find out what that was, I take my previous y value, so that was 0.92, plus the slope at the point in question that we had previously, so 2.4 and 0.92. To find that slope, I would just go 2.4 plus 0.92. I add those together and I get 3.32. That would be my new slope for this equation. And then I multiply that by the change in x, which it tells us is 0.2. Now I just get my calculator out, 0.92 plus 3.32 plus 0.2 gives me 4.44 for my, oops, I put plus instead of times. Hold on just a second. I wrote that down wrong. Times. Gives me 1.584. Okay, so this is my y value right here, 1.584. So now what I would do is I would use that point to estimate what 2.8 is going to be. So 2.8, I want to know the y value, so I take my previous y value, 1.584, plus, we'll find the slope in just a second, and then we'll multiply that by 0.2. Now the way that we find our slope is we take 2.6 and 1.584 and plug that in to my derivative equation. So 2.6 plus 1.584 gives me 4.184, which is now the slope for this next mini tangent line that I'm trying to use to estimate the y value. I just type that in, 1.584 plus 4.184 times 0.2 gives me 2.421, or 0.8. Well, I'm trying to estimate f of 3, so I have to do this one more time. Notice my x value is now 3, so I take my previous y value, because I need to know the y value that goes with it, 2.421, plus my change in x is 0.2, and the slope that I find in this one is 2.421 plus 2.8, 2.8 plus 2.421. When I do that, I get 5.221, which once I do that, I just put that into my calculator, 2.421 plus 5.221 times 0.2. And that gives me my y value that I'm trying to estimate of 3.465. And that would be my estimation. Now again, I've never seen one on the AP test that's that many steps. Usually on the AP test, it's like 2 steps at most is what they'll ask you to do. But hopefully this kind of makes sense when we're dealing with Euler's method. Okay, so again, that formula that we're going to use is y equals the previous y value plus the slope multiplied, plus the slope multiplied by what the change in x is going to be. So what I'm going to do is I'm going to pause this here for just a second. I'm going to put all my work up here, and then you can check your answer with that by trying this problem on your own. All right, so here's our answer for this. Now, this one's a little bit different because it doesn't tell you what your change in x is going to be, but it does say that you're going to start at x equals 2, and you're going to have 3 equal steps to get back to x equals 1.7. Now, one thing to notice here as we look at the answer is we did move backwards. So when we move backwards, our change in x, it's not just how much x changes by, but it's also the direction that it's headed. So you'll notice that my change in x is always negative 0.1, and that's why I have some stuff crossed out here because I accidentally forgot to do that to start the problem. But you'll notice when I started x equals 2, my y value for 2.1 is, for 1.9 is 2.9. So my value for x equals 1.8 was 2.81, and my x value, or my y value in x equals 1.7, which is what we were looking for, is 2.731. So that's the answer you should have gotten on that one. Again, if you accidentally moved forward, you probably got something a little bit different. But this Euler's method, it's not that bad once you've done a couple of problems. It is fairly monotonous, but it's also nice when it shows up on the AP exam because it's not too hard to do. So hopefully that made sense. If you've got any questions about Euler's method, please let me know.